Alright, then I guess I'm just gonna wait a moment to see if any other people happen to join, since,
Hopefully people join, but I think you made a mistake picking Zoom instead of Discord.
Oh yeah, probably. But alright, now I'm just gonna let this wait for a moment and set things up. What? South is broken into north and south. South has two parts, crisscross north and south. There are the north and south sides of south. Okay, I'm going to be sitting in the Zoom call. Don't yell for me. And I'm just going to assume everything there is working. Great. Well, I can't say I'm, too surprised by short turnout, since it's not exactly an interesting subject. However, recordings exist, I guess. Alright, just getting into it because I'm gonna hope this thing's set up right here. Yes, that is. So, dissonance in music theory is a horrendous topic that's barely dealt with at all. People usually just kind of say yes, no, maybe, oh, in this context it is. And, it works well enough for some people's uses, but, it's very imprecise and annoying. So, Euler had the great idea, being the polyglot of every field imaginable he is, he said, what if I make it precise? And, he tried. To any natural number he associated in another natural number to it, given by Gn, which I'm pretty sure he used gamma, but that's used for everything else, so, is equal to 1 plus the sum across the primes of AP times P minus 1. with AP being the exponent of that prime number, and this works because every number has a unique prime factorization. So, you know, this works fine and good and all, until it doesn't, because around 299 over 200, you would think that's close to 3 over 2. That's close to a fifth. It should be small, but it's not, because they extend it to rationals with g of p over q equals g of LCM of p, q. And you can extend it to 3-note groupings, 4-note, you know, however many you want. But it really starts getting larger numbers for more things. And it really isn't very good at guessing how we think things should be unless we already round for it, which is kind of cheating. So that function is an attempt, but it's not very good. An example of this, demonstrate using the formula in the context of a sound. So the obvious example is, you know, so let's say you plug in 1. That's the unison. So 1 is unison, 2 is an octave, 3 is tritive. It's the, you plug in the ratio of a thing. So 1 has no prime factorization, and we just give it the value 1. So g of 1 equals 1. G of 2 is going to be 1 plus the exponent of 2 times 2 minus 1, which is 1 plus 1, 2. And it's going to continue in this fashion. So, like, 4 is, let's see, what was 4 should be like 3. 3 should be 3. It kind of just keeps on going up as you plug in numbers. Yes. So we're talking about harmonies here. Yes. You don't plug in a frequency for the sound. You plug in the ratio of the frequencies. And as Espio said, he has a thing specifically on this function in particular, which, you know, is a lot more in-depth onto this one particular thing. And the point I'm going to make is this function sucks. It works fine and good for like 3 over 2 or 3, and it just kind of, it acts kind of like what you'd think. Bigger denominator, bad. But it does all kinds of wacky stuff with like prime factorization. It doesn't round things, and overall it's not the best. Plus, oftentimes people deal with, we only deal with things up to octaves. So we would number things, you know, 0, 1, 2, 3 to 11. You know, let's say, you know, C, D, E, or not D, but like D flat, D, E flat. So we just count by semitones, and that works well enough to give us our 12-tone equal temperament. And most people just associate something simple like a minor second, bad. Major second, bad. This seventh, those are bad and those are dissonant. So by simply giving everything a yes or no, you're doing the same thing in a sense as what Euler did. In a, in a much more robust form, of course, because you're not giving specific values to anything, but you're saying, you can do this the same by just saying, oh, C, we give C 0. We give D flat 1, D 1, E flat 0. So we put a higher number for bad, which, while that might sound counterintuitive, it's exactly what Euler did, so that resolving things is the same as going downward. It's a bit backwards seeming, but you'd usually want to think of resolving as reducing tension. So it kind of works in that same sense. So it turns out you can do a lot with just this. All you need is just a way to stack your things together and a way to assign them these values so that you can order them, because it's not the specific value, but rather the order of the values. With Euler's thing, if every value is multiplied by 2, it wouldn't change anything. It's still just the comparison that matters. So, the straightforward generalization of this is, what if we can't compare everything? And even though this seems like, why would I ever want to have things that I couldn't compare? You already have that in a sense. You have your little tonic right down here with I. You've got your dominant up here. You've got your predominant up here. But your predominant can obviously go into your dominant because that's the point of it. And we know for a fact that your second also has a bit of a predominant function to it. But the second doesn't usually act as a predominant, so you can't say either of these is above the other. Or rather, you don't want to say this. If you do something like that, you get loops in your things, and for technical reasons, you really do not want that. Especially since that means you'd have nothing that everything goes to in a nice way. You like having a bottom. So instead of having something like that, and you can fill in this tree with your other stuff like your 3, which I have no idea where the 3 goes, since that kind of varies depending on who you ask. Sometimes it's dominant, sometimes it's not. But almost everything is going to go through your V into your I, which is important. Predominant, alright, so F and E definitely don't go into each other very well. So I probably could have used that as a better example. But you can extend this a little bit because, you know, maybe you don't want to think about 2 as being the 5th of the 5. Maybe you want to think of the 2 differently and instead have V of V. And you're definitely going to have to do something like V of 3 here, because that one doesn't usually sit in your major tonic. So, you know, secondary dominants. You can do this and you can extend your tree upward kind of inductively. You put your whole functional harmony of your usual tones and you put them all above your tonic, because everything can go back to the tonic. And I'm pretty sure everything goes through the dominant as well, since, you know, I guess that's the point. But on top of everything you have, you stack a copy of it and you put over IV or what have you. And you put a copy of it and the whole thing just extends upward for as long as you want it to. It's not the best way to do things, but it's a way to do things. And because the entire thing is exactly identical to everything directly above 3, for example, because the whole thing is identical, if you cut off everything below the 3, then the 3 acts as the tonic. So your tonics, modulation is not necessarily anything you can, it's something you can represent as just picking a new bottom within your thing. So it acts as a kind of, with air quotes, local tonic. In this case, it's exactly identical, so every key is identical. Yes, modulation is moving to a new key, but picking a modulating to a new key is exactly identical to working over that note in your original key with the secondary things, because they are identical in the sense that for every element you pick here, like here, you can pick an element here which is identical by just adding a /3 at the end. Whenever you generalize this isn't exactly the same thing, but in functional harmony it is. So turns out functional harmony is great for all kinds of reasons. Who would have thought? So we can call this modulation, but because that name insinuates some stuff that we do not necessarily want, we're going to call 3 here the local tonic of the tree above it. It's the bottom that everything branches off of. So it's the tonic of that subtree. So it's a pretty handy thing to have. Because of these local tonics, you can make, you might want to ask something like, why do everything with orderings and all that, which is, you know, the answer is because it's pretty effective and it's a nice language that already exists, so you don't have to do something entirely new and awful. So, wow, that's horribly formatted. I'm gonna zoom in on this a bit. So you've got fancy symbols on the left, which, you know, I have no idea the people here's background, so I have no idea who here can understand this. As is. I'm going to assume at least one person can. But if A leads to B, as in, if A implies B, so that anytime A is true, B must be true, we reverse the arrows to decide the orders. So the best thing we put not at the top, but at the bottom. The reason for this is a technical condition about how you can fit the integers inside of any ring, and, you know, turns out it's hard to have something at the very top when there's infinitely many things. So, you know. So, the arrow is A implies B. And because we have an element, because we make resolution downward motion, it ends up the same. So that if A implies B, we can go from A to B. If it's at the bottom, this does not technically mean it's the tonic, because, you know, the tonic we consider to be at the bottom of function harmony, but we also have to put empty sound at the bottom, because it's empty sound. Everything can resolve to empty sound because it's empty. So it's not necessarily 0 as the tonic, but it's the best you can get. At the very top, if the top exists, because it doesn't have to, this is a key point, the top is highly or exceptionally dissonant. It's the opposite of the tonic in a sense, like for your normal 12 tone stuff, you could have all 12 notes together in a cluster, and that's pretty crunchy. And because of that, you would consider that as being able to resolve anywhere, unless you only allow triads, in which case there isn't a top. And the backwards E is saying there exists. Upside down A is for all. I don't know how many of you people will ever have to deal with this, but is crunchy a musical term? No, but, you know, dissonance is pretty subjective until you get the formalism in. So the way we do our ordering is we flip everything around. However, it turns out that some logic things actually already do flip the things around. You know, it's not the way you would think, because if A goes to B, you'd expect A to be less than B, but, you know, there's like a historical choice that this is true. And anyway, inf is the infinitum. You pick the lowest possible thing. Actually, it's, sorry, wrong, wait, but the infinitum is the biggest thing that is less than all your AX. It's as close as possible while still being below them. If you have only finitely many things, you can just take, like, the bottom in the real numbers, like the infinitum of 2 and 3 is 2. But things get a bit nasty whenever you have open intervals, since the infinitum isn't necessarily in the set. And the supremum doesn't have to exist here, though. So everything kind of falls apart. And it's not the most useful thing, because even if the supremum exists, it doesn't have to mean anything. So it's kind of just there. So you'd be fine just ignoring this because of that. But it's still useful in a few niche events. Assuming anyone here knows some basic, the antiparticles thing. However, you don't necessarily need one here. In order to formalize these, technically you want a module over a ring with a measure structure on it, with a function which is invariant under the ring action by non-zero elements, to a partially ordered ring that is positive everywhere. And that's disgusting. So I'm just going to draw it. So your module here is kind of like a vectors, if any of you have dealt with vectors. So it's like vectors. They're just things here. For any little thing for any point in your vector, you can multiply it by a number and move it somewhere else. You can add them, you can multiply them by your scalars, which should probably look something like the real number line. So our W here is what we would call the space of our basic musical objects. These things on their own aren't too necessarily that interesting. Like for 12-tone stuff, we'd have the free abelian group on 12 objects. So we just have, here's a C, D. You can add them together, but they're never zero unless it's 0C plus 0C equals 0. So none of the C's and D's ever cancel out. That holds for all the notes. So we just have, there's two C's here, there's a D. So that's how you'd usually do your 12-tone stuff. And that's obviously something you can put over integers. So you have 1, 2, 3. So you can put that over your integers. But that gives you one cluster of chords. So you just have C, D, E. And that's not very useful. So what you instead do is you take a certain formal construction. That is an S, by the way. Fractor script is disgusting like that. So SW here is like taking your W and putting a copy above it, above every single number. But there's only finitely many different points chosen. So these two might be the same, this one isn't. So you have, for every integer here, an associated musical object right above it. So this gives you your formal compositions. And this is obviously a lot more useful than having simple atomic objects, because now you can actually fit music in it. And you can also repeat this if you're insane. So you can have collections of notes for every integer, and these collection of notes are ordered in this fashion as well. Because you now have your function over your line here, you can do more interesting things. So your function here has to behave nicely. It has to put your tonic to 0, which, by the way, you can do this with Euler's thing so long as you remove the 1 plus whatever, because that plus 1 does nothing. It doesn't change the ordering, so you can remove it. Need an integration of vector space for each note. Well, the integration part you can do, but first you would want to have everything work formally first, but you want like something that looks like a copy of your space over every object, which you can do this in a bunch of disgusting ways, but the other way you can do it is just have a sequence of objects like functions over the real line. Instead of having a continuous line, you want it to just have finitely many different points, and it's just changes like that. The obvious example of this that just about anyone here should recognize is you've got the 12 notes and you just put one above every beat. So like a quarter note here, quarter note here, quarter note here, quarter note here. And if they happen to be the same, we could connect them. But whether or not they're connected is beyond what this function cares about. So it just says, this is here. We know what it looks like right here, right here, right here, right here. If you really want to care about how things are connected, you'd want the real number line. So this tells you it goes to exactly here before there's something right here, and so on. The other obvious example that people have probably been waiting for me to bring up is waveforms, sine waves. So your basic musical logics in this case would be sums of sine waves. And you specifically want to have only those sums of sine waves which converge. So you have to restrict that appropriately. And these are special, and we give them, a bold W, which is a bit hard to draw by hand. This bold W is like a canonical example. So whenever you want to talk about them in a sensible way, you would usually want to interpret them as elements of this. So instead of dealing with W itself, you would deal with a function to bold W here. But, that would require actual math to develop, and a lot of time to get into it. But because you have your function here, which gives you W to your domain here, your range here. This is a ring, so you can order everything and you can add and multiply it. So this looks kind of like the integers, except it's not necessarily, they're all in a straight line. They might be branching off here and there. You might have like some very disgusting looking things, but the fact that it's ordered actually makes it really nice, surprisingly. So we have this, and our elements of every element of this can be turned into a function from our time, which is our base ring, to W. So we just do the obvious thing and we put them together. And now you have an analysis of your piece. It tells you what the piece looks like at a point in time t, which is obviously limited because it tells you the behavior only at the point in time t. But even though it's limited, it tells you a lot of information, actually. This cannot in any circumstance ever tell you exactly what omega is, but it can tell you a lot about what it looks like. Because turns out looking what a piece looks like is kind of the entire point of music theory, so it's pretty nice. Even though these things are limited, because you have extra stuff on it, you have a function mu, which acts on your bass ring, which all this thing does is give you a sense of size of sets on your bass ring. It just tells you how big is this collection. So, because you have this, and additionally because where you're mapping to is a ring, you can integrate things. And even though this integration people don't like that, this is actually just a fancy sum. So it's something along the lines of something like omega of like ik. Because there's only finitely many different values it can have, you just take all of the values it can have, you pick out the size of this, pick out how big that area is that each of them covers, and you weight them by it. So if this shows up at a size of 2, you add it twice. Yeah, it's kind of an area thing. Not exactly, since, you know, we're kind of like going back and forth between like W and all kinds of other disgusting things. But this is pretty handy. Knowing this is strictly weaker than knowing the behavior of DW, but doing this gives you a sort of local behavior. But one thing that is not strictly weaker than knowing d omega is knowing this little thing. So to any set, or any reasonable set, you can look at how omega looks over the whole set and flatten it. So you flatten omega across the whole set. So if it takes on the value of, if it plays a note D and a note C, even if it's separate times, you add D and C together and you smush them down regardless of the time information. And you act on everything in that area as if it was all pushed down into a single point. This gives you a surprisingly large amount of geometric information, because you can know how it looks here and how it looks here. But because even though you know how C looks and you know how D looks, that doesn't necessarily tell you how, C plus D looks. So those two things will look different in general. So knowing how it looks here tells you more about how it looks here. And it's actually very difficult to figure out what omega is, but that can give you something that tells you what it is in a much stronger sense. But knowing the integration part and the flattening part together don't tell you everything per se, but a lot more. So your entirety of information in your music just relies on how things go downward in R and upward. Your tau variation tells you how, if everything was clumped together, where it is. your sigma tells you, which is the integration part. Sigma tells you how it behaves over that area when you weight by importance. Because tau here, everything is equally important. Sigma here, some things get thrown away entirely. And funny enough, tau, despite being a pretty sensible thing to just say, oh, you just take everything that appears, doesn't work whenever you start allowing more than finitely many different values, but it's good enough for reasonable purposes. Even with all that information, you can still only do so much, since your function D doesn't distinguish between, C or the same note twice as loud. Even though, those two things are different in that, it would have different timbres on your instrument. This twice as loud is referring to like the exact waveform of the sound is exactly twice the amplitude. No changes to timbre. There's some idealized stuff going on here, which doesn't occur in reality, but that's math for you. With all this, everything starts looking disgusting because you've only got rings and orderings and measure stuff, which doesn't necessarily play nice with the ring, though it should. And if you're working with anything that doesn't, it's stupid. So the obvious answer of how to deal with that is you can consider a fairly weak notion, which you take stuff from 0 to 1 and you put it in T. And you want it to respect the way you decide size. You want it to play nicely with that, so that if you can decide the size of some group in T, it's going to be something you can determine the size of in here. And even more than that, you'd want it to be not just something you can determine the size of, but you want it to be something you can determine the size of easily, like A, B, cup, C, D, or something. Like, you want it to play very nicely with intervals and not some crazy measure theoretic shenanigans. So having a path like this gives you your realizations. Realizations are your these are functions from 0 to 1 to W, which is strictly larger than the functions from T to W, because for any T to W you can just chain them together and circumvent T entirely. What about frequency? The frequencies and such information would be in W. T is just where. And working with the real numbers, turns out being able to order things is very strong. And additionally, the real numbers have a sense of closeness. They also have all kinds of crazy other nice properties that you probably take for granted. So you can make things a lot less awful by working with these things. And you can even, you're going to want to consider those things such that you can pick a W or an omega such that it factors like this. But whenever you want to talk about extending something, like you start with a little motif and you want to extend it longer, you will in general have to cut T out of the middle, because there's like conditions about how many values you could have on T, but if you're doing something that requires it such that you cannot pick an omega, you're doing something horrible that you shouldn't. But, you have to reconcile that possibility if you're working with particular ones. So this lets you deal with stuff in a more reasonable sense, because you can say it acts like A, then B, then C. Because T, you can just say where. This lets you say things in order, so it's I, then V, then I. Because, you can order the real numbers. But there's an even stronger condition you can do, which is not, I'm pretty sure this is not a strictly stronger thing, but it's a very different thing. You already have your W to R here. And that tells you how things relate. But you can't always compare everything in R. And W probably looks horrible because it's only a module and not a vector field or vector space. So what you can instead do is you can map everything to your bold W. And you want this to respect your addition and integer values. But everything else is kind of fair game and it looks horrible to deal with. But you want to deal with things which act nicely under addition. And because this is W here is over the real numbers, and we map the function here to real numbers, all you need to do is something like this. This square is probably not commutative, since this little arrow here doesn't have to actually exist formally, but it exists at least where we put W in at. So instead of dealing with all kinds of crazy shenanigans of is 3 greater than or less than the letter A, we just all associate them with a number, and every object with a waveform, and this is how any actual implementation would act. So W is a module, which I have no idea what your background is, Aiden, but W's a module, so it looks kind of like vectors, except you don't necessarily have some nice properties. It's like a vector space, but you allow things to maybe loop around. Sometimes finite dimensional things, if you look in, it's no longer finite dimensional. Things get disgusting. This R here is a partially ordered ring, which means it looks like the integers, but awful. This here is the real numbers, which, I'm going to hope you know what those are. And bold W is waveforms, so like it's sums of sine waves and such. So like saw waves are in there. If you can, it's like instead of dealing with stuff as arbitrary objects, we turn them into sounds. So we're no longer dealing with the music directly, but rather indirectly by acting on the sounds. And the AVI are actually the AVI that you'd be used to. So this thing doesn't have to be strictly the way. This diagram is a big abuse of notation, by the way, because drawing it like this is technically cheating, but it looks like this anyway. So the tree I drew before, you have your your V, and everything branching off, and the trees themselves branch off in identical copies. The way you'd map this here is you're going to pick some base object for your ah. So you could just flatten it horizontally so that this whole thing goes down. You could do something like that. And for if you do something different like your C and C sharp, C double sharp, if you don't identify inharmonics, whenever you map to the frequency space, you're either going to maintain your not identifying inharmonics, or you're going to identify them. And whichever way you pick is going to change how you look at things. But you can do a lot more by passing to sounds, because you're dealing with how it sounds more so than how you want to think about it when writing. So you can do more computer assisted things that way if you have the framework set up. This thing as a whole it seems limited because you can't pick out omega uniquely usually, and in fact never, unless you have some very, very unique circumstances. If you can pick it out uniquely, you're doing something crazy. Even though it seems weak in the sense that all these conditions seem to generalize things unnecessarily, and while they may be generalized in a very strange way, you can still do a large amount with them. Because with the logic diagram drawn earlier, these things look kind of like a formal system for logic if you add on a little bit of extra logical symbols. The interesting thing is you can go backwards. From any piece of music and your analysis system, you can get a formal system, and such that composing is actually equivalent to looking at interpretations of your system in particular semantics. Similar to a Laplace transform, but one for sound. Laplace transform. I don't deal much with Laplace stuff, of course, but even if it is similar, it's likely not quite the point. Since the point is to, from the music, derive a formal system, and from the formal system derive music in a way that's compatible. Anything you draw... Oh, anti-tonic? It's in air quotes because it doesn't necessarily exist, and it's more of a vague idea than something that must exist. Instead of everything resolving to the tonic, everything goes away from the anti-tonic. Yeah, it's kind of only here for completion's sake for the logic analogy thing. Okay, for the to change the transformation. Suppose it is kind of like that in a sense. Instead of dealing with things in not frequency pitch. Instead of dealing with things on a time parameter, you deal with things on a frequency parameter. I think is that or Fourier? Anyway, you want to change the parameters. Instead of dealing with things on your probably horrifically twisted ring, but instead you want to move it to the real numbers. Instead of dealing with things on your very spiky module, you want to move it to sine waves. I'm not sure it's quite the same thing since we're not doing it in any invertible sense, because once you go from your spiky module to sine waves, you can't really go back unless you know what it is already beforehand. And at that point, it's unnecessary. But this logic and formal system, going from the music with the ordering to a logic system, is compatible. If your music follows a few extra rules that you add on top of the fact that you want things to go from dissonant to consonant, if you add on a few extra rules about what's allowed here and there, you get a formal system with a it's more Fourier-ish since, you know, ha-ha pitches, but it's not really differential, but like ordinal. So for anything you have your ordering here, you know, what have you. So the things which map to here, the things which map to the left, those that map to the right, you can bundle those together into B, C, A, and clearly you have B to A, C to A, and you do have there is some X such that phi X with all that. So you do get these things if you add a few extra symbols in for, if you add a few extra symbols in for this, This one you define as part of it already because it's based on how you can derive things. From any piece of music you have composing this, it's going to draw out. So even if your original tree looks something like this, you're going to draw out a specific little patch of it with whatever piece of music you have. You draw out some specific little patch of it, and, you know, it's going to look possibly horrendous if you don't have a bottom to it too. But, oh yeah, the chemist thing, of course. So from this, you obviously get the points. Yeah, you've got the points here, here, etc. So for any composition in your system, you can get a system out of it if you, a formal logical system, if you throw away like the very bottom, add a few symbols. And from any formal logical system that behaves like this, because you do need a bottom, you do need things to be downward directed. Like there has to be a few conditions on what your systems are. You can get a system to compose music out of. And any piece of music you get from your system that you get from a piece of music will give a system related to it. So these two operations are semi-inverses in the sense that they're like adjoint. It's weird because they use adjoint and adjunction, which come from different roots. But so from your logic systems, you can go, if you iterate and you go forward and then back, because, you know, every piece of music gives you a forward way and a backwards way, and the backwards way is always there. It looks kind of like an adjunction, which in order to make it an actual, you'd have to you'd either have to show that these things hold universally. So I'm not going to go as far as to say it's an adjunction because that's a lot of work to show. But they are weakly inverses of each other because if you apply it a few times over, you get really close to the original, going back and forth. And with this, instead of looking at music as if it was in system A, you can look at music compared to each other by looking at them in the systems of other music. So you could take Bach, break it down into a formal system in this fashion, and then move something from Rachmaninoff into the system and examine it. And, you know, the other way around, and these two should be compatible in a sense. Of course, you know, the compatibility might be something mostly vacuous in actual information, but you can compare these two in their own systems, or instead of studying them for 50 some odd years to compose like them, just draw up a formal system that gives you the exact rules you would need in order to sound like that piece. You apply this to a large selection of their pieces. You find a common base subsystem underneath them that goes into them all uniquely. Haha, local tonic looking. Looks familiar. And from this base system, time issues. Which one was the time issues? What about time issues? Which part was that again? Well, I mean, you know, it takes a long time to show some of these things, like the adjunction, and it's not quite exactly an adjunction unless you compile everything together into some single operation. And with the realizations, they don't necessarily always factor through the time thing like you would want them to, because, you know, not everything can go through them. Compare them. Does timing matter? Well, the timing is actually almost entirely encoded within the little mu thing. Not exactly, because you also have order stuff, but, you know, if you're any kind of sensible person, you're going to put them over something equivalent to the ring of integers, which has an ordering on it. So timing is built in, more or less. Give or take your specific choices of what's what. If you put them over the reals instead of the integers, you know, there's a few specific choices you make, but those are conventions you would make, and you'd have to be consistent among them in order for things to have some coherency between them. But, you know, so long as you do things like a reasonable person, you'll be fine. And, you know, let's say let's say you have some pieces of music of Bach's, you know, like omega and nu here, and we denote their the system you get from it with F or something. So these two systems exist, and if you want a system for Bach's compositions in style XYZ, you'd pick something down here, which may not be the system of a piece in exactly what way, and you want it to be able to fit inside both of these. I think the specific condition you'd want on that is for those two to be elementary extensions, in the sense that it's true in this one if and only if it's true in it's true in the bottom if and only if it's true in the top elements for both of them. so that any sentence you can anything you can formulate that's works on the bottom works on the top two. So in that fashion, it is a common system so that both of them are in the same style of the bottom, though they might have other stylistic subtleties upon them. They both have a common root style. However, if you pick two things of very different styles, you're going to get something that's like, you can put a tonic. So you do want to be careful there, because you might get no actual information out of it if you pick wildly. And actually computing any of these would be an absolute nightmare, because of I'm not about to sit down and make a formal system describing exactly what is and is not allowed in Beethoven's Ninth Symphony, but the point is that you can. And because, you might get a masterpiece or you might get nothing. Nothing is allowed. And because, computers exist, and every little bit I've described, so long as you pick your conventions beforehand, because a computer can't do that. You're going to have to say how the timing system works, how mu works. You're going to also have to additionally specify how to interpret the notes off the page, because it's not going to know that this pixel here is E. You're going to have to give it symbols. But once you encode the data in a format the computer can read, you can do this automatically. Finding this one here at the bottom, I have no idea if you can do that one automatically, because I'm not a super expert on formal systems. Because, at that point you're diving into actual math logic, and that is not something I am a master of. But you should be able to get something automatically that looks like that. And, whether or not you get the exact perfect right bass thing, it's kind of, unimportant, since you're probably not exactly completely right with the way computers automatically do things anyway. And since composers tend to not like being told what to do, they're probably going to break the stylistic guidelines here and there anyway. So, if your computer somehow has an implementation of all of this crazy stuff, which is a bit wild considering, you'd need some pretty custom stuff to set this up right. I'm not sure if Sage or Macaulay 2 can run these things. You're gonna have to get a bunch of setup, but assuming you can do all this right, you can get something which is near this, and this extra little system you get here will look like a base system for both of them. So hey, automatically generated Bach that is exactly in a common style. Not just AI neural network generated, but literally the same style as far as the computer can tell. Which, is interesting. Impractical, but interesting. These things are, of course, to actually capture the details of the style, you need to pick your conventions correctly. That's basically the meat of the thing anyway, but then the computer can analyze however many you throw into it automatically, which is the time-consuming part. Not so much the hard part. Also interesting is these formal systems, you want them to be precisely those that you can pick with a few extra. You'd need a few extra conditions as to like what symbols you have, and you know, those are formal conditions that no one here is going to care about. But you also want it to be able to fit as a poset in here into your ring. And you have to have it so that you actually want it to be like the opposite version. You can throw away a top element because the top element has a lot of problems. So you throw away the top element, which is actually the bottom element, because you've already inverted everything. Or it's the bottom element before you invert things. So you get rid of that, and you want it to fit inside this ring in an embedding in precisely the positive cone, because everything's positive valued. And you want it to put the formerly top element into 0, the bottom element. And being able to do this gives you a system, because you already have your objects, and this picks you already have your objects, your formulae, and this picks your D function because you embed it into here. So, you know, that's something. You'd have to jump through a few like formal hoops to say like, oh, turn this into this poset, put it on an abelian group and module it up, but you certainly want your system to be able to be put into here. Otherwise, you're looking at the wrong system, because it cannot be the result of any operation of this fashion. And I have no idea what posets can precisely go into this, because it turns out that's a hard question to answer. Like actually it's not like, oh, it's obviously this XYZ, because partially ordered rings can get a bit nasty with the way things work, because the order has to be compatible with the ring structure. So, you know, that hurts everything. Also important is this is going to be your interpretation of the system. So this P here is not just, oh, you take the system and you turn it into this, because you can't just say, oh, A, put that here. You can't really do that. You have to take A and like turn it into something else by the way of a function here. And this function gives you semantics by putting it into a poset for your ordering. So the truthfulness, so, you know, you can have A implies B because B is less than A whenever you order them, right? But you might not be able to show that B can be derived from A. Double stroke arrow is semantics, and single stroke arrow is syntactical. So with the formal system you get, you'd be giving syntactical information by saying, if you can do XYZ from ABC, then ABC derives XYZ. And you and you add your little arrow here. However, it's entirely possible and, kind of likely that something along the lines is going to make everything hurt, because logics are wild like that, like a Gödel's incompleteness theorem. If you can do arithmetic, which, by the way, if your system's strong enough for arithmetic, I don't know what you're doing. You're doing something crazy. If you can do arithmetic and your axioms are recursively axiomatizable, then you're going to have something such that it's true as given by the interpretation here, but you cannot prove it's true. So it would be admissible in your interpretation in that it would map to your tonic, but it would not be the tonic. They behave identically, but you could never write them the same. So suddenly inharmonics are no longer equivalent. And, sometimes you might have something which is implied, which lead to them in the poset thing, which you don't have with the syntactical thing and the other way around. But you generally only deal with the system such that these two play nicely together. So, if you can derive B from A, you want them to be less than each other in the interpretation. You can fit that in as an axiom of it. In some systems, there is no interpretation. So they're dead systems, and you cannot do anything with them in this fashion. But, I have no idea what you're doing if you end up with one of those. Let's see. There's you actually get a lot of stuff on this, because having your mu here and your d, which is invariant under your ring action, your module over t here, but t also has a measure space here, which mu is a function of to here, and it has to behave nicely along with adding them together so that it acts kind of like the size you would think it should act like. And there's, it gives you a lot of structure. Problem is, you want to decipher what structure is musically relevant to whatever system you get that's from this. But with all this, merely assigning what's nastier than what gives you an entire theory of harmony out of just that. So it's kind of unsurprising that functional harmony has a lot of stuff in it, since you have like all kinds of wacky duality stuff. Of course, you can't just do functional harmony naively. You have to break a few of the lines, because if you have any circles, loops in there, it's nasty. And
Mason, I gotta go.
Okay.
You hopefully send me the paper soon. Have you worked on it?
I've got notes scrawled all over the place, but not like an actually written paper, of course.
Okay. That would help me some. But I've got my notes and to review. So I'm going to be looking over it, and so I'll send you some questions hopefully by the end of the week. Is that all right?
Okay.
All right. Good job.
Okay. Nice. That went well. Yeah. Turns out loops suck, by the way. Oh, man. Who is over here pinging me over here? Oh, it's the group chat. Thanks. Yeah. I mean, at this point, if you wanted to actually continue working with this for any longer, you'd have to actually get into the math more than I have. Since, you know, with the associated logical system, you'd have to prove that these things remain consistent and completeness. See, the point is, the problem is it's not too effective in the sense that it's a lot of structure to get what it is. You know, you've got, like, in order to define one of these things, you need like 7 objects, and they all depend on each other. Like you need the base ring, the module that it's over, the target, which, by the way, has an ordering associated to it. So whether or not you consider that as part of the information you have to define, which, you know, you kind of do, you also need your collection of measurable sets, which have to behave nicely under interaction. You have to have this. You have to have the D function, and you also fix a tonic, because, you know, it's kind of helpful. I guess you could probably throw that away pretty easily, though. Since, I mean, if you want to do something atonal, just tonal be gone. Doesn't take a lot of effort for that. It's not the most efficient way to go about these things, clearly. And any practical implementation of it would be computational heavy, because you'd have to decide the implementation, get the computer to understand the implementation and the data in a way that reading it's reasonable. And then it has to give you the information about what system's allowed, which requires probably a lot of memory storage and ways to decide what is and isn't an important part of it. But something. So you can pretty much develop an entire theory of harmony about just saying, haha, this is worse than that. Which, you know, is interesting. Because if you just throw away the mu and m, you can no longer integrate things. So it no longer becomes possible to determine unimportance. And in fact, having the realizations is actually kind of dependent on that, because you want things that are important to remain important, but you can determine unimportance in the realization independently of it. So now you'd have to look, your realizations, you can no longer just like say, this is unimportant, therefore it's unimportant. Oh, the speed of the computation? Give me a second to think through this and what I think it should at least be. You know, it should... big. Like, this is going to depend on your choice convention here, but like, let's just say we put it over the integers and like counting measure, because haha, 3 elements. If you count in as the amount of, well, I think you might need like 2 variables, since it wouldn't be just the length of the piece, but also the number of things in it. So, you know, you have both of those. So, yeah, I can't foresee this being fast at all. Since you'd have to run through, like, every collection of notes in it that are close to each other, and, like, this leads to this, and this, in fact, leads to this everywhere, so it must be a rule. So you'd have to pick, yeah. I'm going to take a wild guess that it's at least NP. But, you know, non-polynomial. In fact, I have no idea if it's even NP. Because, you know, you might have to do like something exponential. But on the plus side, you can do it at all. Autobach. Roll out. I have no idea how large the time will be, but you know, I wouldn't want to, you know, sit around and wait for it. Unless it was like some short thing. But then if it was a short thing, you could just do it by hand faster, so what do you know? Oh, by the way, this system is insufficient for counterpoint, as far as I can tell. Enjoy that little bit of information, because you also need to be able to tell how far away things are, and you don't have that. And that's unfortunate that it's insufficient, but you know, you can add onto it by just like saying, haha, you have a function that gives you the distance between some kind of basis looking set S. You extend it across the one-dimensional subspaces you get from those. Apply some conditions to make it look like a metric, or at the very least a pseudometric. I have no idea what's best here, since I've got some ideas sketched but no actual work on it, and I don't intend to work on it anytime soon right now. You apply that to that, and you can then get complexity of an element by taking the minimum size of elements of S that needed, and you'd want to minimize such that all this wacky, stupid stuff. And then you could look at the contour by looking how D jumps around, because you want D to be valued in integers, I think, because intervals. So you can look at how things jump around here. And you can assign a function, let's see, what was the thing I had? I think it was psi. So you can assign a function, if I can select it, a function here based on some epsilon that's like the distance between omega at point in time t compared to omega at point in time t plus epsilon, and you look at the distance and how it jumps around that way, and then you do something like this. Also, I think you want a realization in there too, so that, you know, it's actually on the real numbers. You do this dx, where the dx being, I have no idea if Riemann integration is even sufficient here, or if this limit exists at all, but you then have lim as epsilon goes to 0. And this gives you a sense of the contour of it. So the bigger this number is, by the way, well, no, you don't want psi to be this. You want to include like a sign convention so that it's so that it's negative if and only if the value is 1, positive elsewhere. So, you know, like if it's 1 step away, so you want to be positive if and only if it's like 1 or 2, or, you know, I don't have the details working out completely because I haven't exactly worked on it too much. But with that sign convention on it, if this thing is greater than or equal to, if this thing is greater than or equal to 0, then your thing sucks. And it's way too jumpy. Sorry, that's how it is. I mean, you know, greater than 0 or less than 0, you know, that depends on the sign convention you have. And I have no idea what the correct sign convention is or what the correct condition is for D to make sense here. But you can, using this, you can decide, you can quantify and qualitatively say this must be admissible. This realization must be admissible here. You restrict it to those realizations which factor through some omega, pass it through this, and you can say this is a contrapuntal realization. And this is going to depend on how your realization is, because moving things around might change the measure. I have no idea. I haven't worked with it enough to tell you for sure that it doesn't matter. But if it doesn't matter, you can throw out the realization and just do it on it by picking one at random. Oh, and all of the, even having this is insufficient for extending a given composition. You're going to have to like pass to like a system and then pick something that extends it in that system with like back and forth action, and you know, I would not want to do that. So I did not work with that yet. Any questions on here that I probably might be able to answer? Oh, that's an unfortunate name. What's going on? If you can see this poorly drawn MS Paint drawing, you can probably see that something is going on that is disgusting. Looks mathy, it is mathy. So this whole thing has been, yeah. Yes. Because it's inclusive or. But so TLDR. You've got a dissonance function which says how nasty things look. By having this function and you order things, you can develop an entire theory of harmony around it. Additionally, you're going to want to strap on something that tells you how important things are based on size, and you're probably going to strap on a tonic because tonics are pretty nice to have. From any piece of music, if you can put it into some system, you can get a system out of that music, and any music you put into that, from that, you can go back and forth, and they're compatible in a coherent way. Not quite an adjunction because it's not quite unique, and like it's a bit disgusting in that fashion, I feel like. I'm not about to go out and find the exact condition to make it an adjunction. This whole system is insufficient for counterpoint, so in order to make it sufficient, I think you only need to be able to tell the different distance between some, you know, further, even more atomic elements in the middle of it, and Yeah, everything looks awful at that point. Is that a good enough TLDR for that? Oh, and also it looks like logical systems, so you go back and forth through that. So, any questions? And answer the probable question that at least someone's asking. Yes, this is ridiculous, and you can probably do all the stuff just, informally by looking at it, but turns out doing things formally takes an extra step or two, and is like the entire point of entire fields of math, as it turns out. I have no idea what is exactly sufficient or necessary for extending music, but I do know that doing it in general requires you to pass to realizations in all likelihood, and that's annoying because you don't actually get something that exists in your system because you have to go one step outside of it. Also, any theory of counterpoint in this is very limited in the sense that I have not developed it in any fashion yet. But given how much stuff you actually have strapped onto this, it's probable you can get a lot of stuff about it. Well, that's about all I have right now, so have fun. A good night if you're in America. And my apologies for making you sit through this.